Now, here I'm going to start with a new topic, and I'm going to spend just a little bit of time discussing the other end of the transmission line. So far, we've spent quite a bit of time trying to understand what happens when I connect a load, but we haven't said too many things what happens when I connect my source. And my source is important, is represented here by the Steverin equivalent circuit. It's really important because this is the one that is going to launch the incident wave, the V0 plus times e to the negative beta z wave in this transmission line. Now, I have all the mathematical details in my notes, so I'm not going to go through and discuss them here in detail. I'm only going to highlight some results. So the first thing I'd like to highlight is that once you have both terminations known, both the source as well as the load, you can essentially find all unknowns, including the V0 plus that we had considered known before, but we really didn't find it. How can you find the V0 plus? Well, all you have to do is apply the boundary condition at this end of this transmission line. So essentially that V0 plus will have to be equated to the power division, or rather to the voltage division that is caused by this circuit that you see right here. Again, I won't go through the detail. You can find the equations in my notes. But the end result is quite interesting. So the end result is shown here, where I'm basically calculating the power that the load will absorb. And now you can see that this is a function of Vg, the known voltage source, the transmission line characteristic impedance Z0, the impedance of the source, Zg, and then two reflection coefficients, the gamma L, which we have seen before. Again, gamma L is the reflection coefficient of the load, ZL minus Z0 over ZL plus Z0, as well as a new reflection coefficient, which I'm calling here gamma G. And that's the reflection coefficient that depends on the difference between the impedance of the line Zg and the impedance of the load, and the impedance of the, the impedance of the source G and the impedance of the line Z0. So that equation, again, is very similar to what we had seen before. You might recognize this term here. Essentially, that equation has been calculated by taking the incident transmission line, the incident wave, and subtracting the reflected wave, and then replacing that V0 plus with the excitation knowledge. And so that V0 plus has basically been replaced here. So this is one way that you can calculate the power of the load, essentially by taking the incident power and subtracting the reflected power. There is also a second way you can calculate the power of the load by just literally looking at the voltage of the load and looking at the current of the load, and then applying the well-known equation VL IL complex conjugate and taking the real part. So when you do that, you will find this second equation here, where this second equation again is a different expression, but it's basically it's actually supposed to give you exactly the same result with the expression here. Which one you use honestly depends which facts you know, but you can basically use any one of the two.